All the presenters, everyone that attends this conference is so friendly, so willing to teach, so willing to learn from you too. So it's not just watching these videos, it's kind of getting that insight afterwards and around at dinner, at drinks, like all the other aspects of the conference besides just like that technical information.
All right, thank you so much everyone for coming. I understand that I'm all that stands between you and dinner, so I really appreciate you making it. But I think we have some really interesting stuff to talk about today. I'd like to make this interactive, so if you have any questions, please feel free to raise your hand and ask during the presentation. But I think we should also have some time for questions towards the end. So hi everyone, I'm Ben Brock. I'm a research scientist at Intel Labs inside our parallel computing laboratory, where I work in our AI software group. We work on compilers and libraries for AI and other large-scale problems. And I specifically work on distributed C++ data structures and algorithms, specifically for kind of HPC type scenarios, where we want to offer a high level of abstraction, but still get reasonable performance running across multiple nodes or multiple devices. So what I'm going to talk about today is this thing we've been working on called distributed ranges, where we try to extend the ranges library to support data that is distributed over more than one memory locale. That could be multiple nodes in a cluster or multiple devices inside a single node. And then to basically implement, we're not all the way there yet, but implement the ranges library. So the algorithms, the views, so that they all work together. This is my obligatory notices and disclaimers. I've been told that if you stare at this QR code long enough, you can see Albert Einstein. But here are my human readable disclaimers, right? The views in this talk are mine. They don't necessarily represent my employer. This is a speculative academic style talk, and I'm not describing anything about future Intel products. I probably don't know anything about future Intel products. And I work in the research labs. So I'm talking about experimental prototypes and early research. So parallel programming is hard, right? This problem of taking your code and running it across a cluster of computers requires a lot of work on the user's part. And parallel computing is getting more and more necessary as our systems become more and more hierarchical. If you look at a modern kind of server box, right, you'll typically see a layout like this system diagram on the right. So you have one or more CPUs, you have some GPUs. These are connected with a kind of high bandwidth interconnect. But to get good performance, users are still going to have to manually split up data amongst multiple GPUs. And this creates a lot of burden. And so we think it's important to have high-level mechanisms like distributed data structures that will help ease some of this burden in distributing your data and then computing over this distributed data. So if we look at this system, right, as I was saying, you've got 4 GPUs. So even if you're just on one node, now you need to think about these 4 different devices and what they're doing. And as our devices get bigger and bigger, the devices themselves are becoming hierarchical, right? So if you look at recent GPUs, they have things like chiplet architectures. Some CPUs do as well, which gives them NUMA characteristics or even essentially their own memories, right? And it's most efficient if one of these tiles of the GPU is accessing its own memory as opposed to the memory of its neighboring tile. And so if you want to get the best performance, you now need to think about where does my data live and how do I partition my data across these different memory domains or memory spaces. Okay, so we want to solve this problem of basically taking high-level standard C++, having distributed data structures that will automatically distribute the data, and then achieve high performance both on these kind of multi-GPU and NUMA scenarios, and also on multi-node execution. So basically, we take something that looks like this, right, written in standard C++ using ranges, and then execute it on a supercomputer. This is an outline for the talk. I'll talk quickly about some background, both just some background on the ranges library, so we're all on the same page, and what's in the library today. And then I'll talk about parallelism and distributed data structures, how we can build distributed data structures in C++, and then we'll go into the actual concepts that we're relying on, how we implement on top of these concepts, and then how this generalizes to some more complex data structures. And then we'll have some wrap-ups, some lesson learns, and some wish lists for maybe a future ranges paper. So let's talk about some background. So in standard C++, I would argue you essentially have three components, three tools in your toolbox that help you implement a program and then in standard C++ and then run it on different architectures from different vendors. So you have data structures, right, which hold and organize your data. You have views, which are lightweight objects that typically represent kind of transformations applied over your data, although they can just be like representations of freestanding functions. And then you have algorithms that operate on and actually modify the data. Right? Let's talk through this example here. So we're using two views, a zip view and a transform view, and then an algorithm, a reduce, to perform a dot product. So what we're doing here, right, is we take our two inputs, our two vectors x and y, we zip them together. Now zip is a view, so it doesn't actually perform any computation. All it does is create a semantic representation of these two ranges zipped together. So what you're going to see is effectively a range that contains a pair that has references to x and y, right? And so when you access those, you'll be accessing the corresponding elements of the vectors x and y. We then can perform a transform using an element-wise multiply. So then we take each corresponding element and multiply them together, right? This is performing that element-wise multiplication of x and y, and then reduce all of them together in an algorithm, right? So together, this performs a dot product operation, just using standard C++. Now, the thing that holds all of this together is iteration, and more recently, the ranges library, which formalizes some of these concepts. So the ranges library formalizes iteration and also ranges, which are objects that are collections of data that you can iterate over. The nice thing about the ranges library and the algorithms is that they are extensible. So execution policies can allow parallel execution. Here we're using the par unseek execution policy, which basically tells our library that it's free to parallelize this algorithm and compute it in an unsequenced fashion, which basically means a vectorized fashion. And also, the standard allows implementation-defined execution policies on top of this, right? So what multiple hardware vendors have done is go and implement implementation-defined execution policies for their devices. So for example, from Intel, we have an implementation of standard library algorithms called 1DPL. And we have a device policy, which represents execution on some SYCL device, right? Which could be a GPU, or could be a CPU, could even be an FPGA. And then we can basically take the standard C++ code and run it on a GPU. Now, there is one thing that I want to kind of posit here as a caveat, which is this question of where is the data? Here, we're kind of glossing over it, although we'll try to get a little bit more formal about this question of where the data is later on. But it's important to keep in mind, right, if you're going to be executing on a device, then you're going to want those ranges that hold your data to be in devices that correspond to where you're executing, right? So if you're running on the GPU, you want your data to be on the GPU. OK, so C++ 20 added the ranges library. And a range is a collection of values. And they're essentially, they kind of bind together these three different things that you can do. You can iterate, you can use an algorithm, and then you can have views over your ranges. There's a hierarchy of different kinds of ranges, right? Which correspond to the different styles of iteration that you have, and also a few other categories like size ranges. And these categories are essentially refinements of the lower types of ranges, if you will, that add additional features to them. So for example, a random access range is a bidirectional range that also allows you to access any element in constant time. A contiguous range is a random access range that corresponds to a contiguous block of memory. And for parallel computing, we're mostly going to be interested in things that are like random access ranges, because it's useful to be able to split up your data into chunks and access any chunk in constant time, right? So that you're not trying to access like a singly linked list in parallel. Okay. So let's talk a little bit about parallel computing and get on the same page about how we're going to communicate and move data around in a parallel program. So typically, we're executing on a collection of nodes or devices. These devices are going to be connected by some kind of a network. And then they're going to perform computation and communicate in order to process data. I did a CppCon talk back in 2021 on distributed data structures in C++. This section is a little bit of a recap of that talk, but I discuss kind of in more detail there. But very briefly, there are two kinds of communication mechanisms that you can use for executing over multiple nodes. There is message passing, in which processes send and receive data simultaneously. So we have node number 0 here, which is sending some collection of data, and node number 1, which is receiving the data. The key to message passing is that the processes typically have to be aware of the other process that's sending the data, right? So both process 0 and process 1 say, yes, I would like to send a message. I would like to send it to process 1. And then process 1 says, I would like to receive a message from process 0. So the key is that they're both participating here. In contrast, RDMA, or remote direct memory access, allows processes to directly read and write into other processes' memory. So for example, if I have 2 nodes in my cluster, one is node number 1, and node number 1 has exposed part of its memory as a shared segment, node 0 can say, hey, I would like to write the value 12 into this offset in node 1's shared segment. This is what this might look like in your code if you had a kind of remote pointer API, right? And the key here is that process 1 doesn't participate in these remote writes. I would argue that building these kind of RDMA-based distributed data structures is kind of fundamentally more fitting to the way that C++ thinks about memory, right? Because typically we have memory and then we have ways to write over that memory, as opposed to having these additional constraints that people are sending messages back and forth. So we're going to be using RDMA to build distributed data structures, or RDMA-like primitives, where we have these special pointers that point to data that might live on another device. When thinking about how we might implement something like this, we're typically going to have a class or a struct that is a remote pointer. And essentially what this is going to contain is some information about which process or which device this data lives on, which we're going to call a rank, and then an offset within that rank's shared segment. We can then go and implement all of the normal memory communication operations that we would expect, like memcopy, for example. And then whenever we need to perform these operations, we're going to go and call into a communication library, which is going to perform an RDMA primitive, right? So if we're using MPI's one-sided protocol, which supports RDMA-based operations, we might call MPI get, which is going to get a collection of bytes from the target buffer on this remote node and copy it into a destination buffer on the local node. Now, we can also make these remote pointers iterators, actually. So we can add a dereference operator. And then the limitation here is that we can't return a raw language reference. The reason for this is that this memory lives in another memory space. It doesn't actually live in like the C++ memory land of normal pointers. So we can't get a raw language reference to it. What we can get is a proxy reference, a kind of smart reference that represents a reference to that remote memory, right? And then inside of that remote reference, we can go and implement an assignment operator, which will write to that reference. So that would if we have a remote pointer from somewhere and we want to write a value to it, we would end up copying some data to this remote location. And then if we want to read from it, we can implement a implicit conversion operator, which will read the data and return it to the to the local node. This does limit us to trivially copyable types because we're depending on memcopy, right? You can't have like a string that has like dynamically allocated memory associated with it with this simple model. There are some tricks you could do to actually represent more complex objects. And I talk about those in my previous CppCon talk, but we're not really considering those today. Okay, so just to recap, right? We're executing in this domain where we have data which lives on different nodes and different kinds of devices. And then we have remote pointers that we can use to represent that remote data. These can support memcopy, copy, atomics, all the things we would expect from a normal pointer or iterator in C++. And they can support dereferencing with proxy types. And like I said on the previous slide, they're limited to trivially copyable types. Now, I want to stop for a moment and reflect on exactly what these remote pointer things are. And also to point out that they do not fulfill legacy random access iterator, or as it's called in the standard CPP17 random access iterator. In fact, they don't even fulfill legacy forward iterator, because legacy forward iterator requires that when you dereference the object, you get a raw language reference. Right, so that's a sad face. However, the ranges library is designed differently, right? So ranges deals with things where you might not actually have underlying data. So if we think about just one of the views that we might have, which is a zip view, like we saw in the previous slide, here what we're doing is we're taking two vectors and then we're zipping them together, right? If we return a single element of this view, what is the thing that we're getting back? Well, it's a pair of two elements from those previous vectors, but it's actually a stood pair of references, not a reference to a stood pair, right? So we've already broken this requirement that we have chi ampersand as our reference type. So the new iterator concepts that we have, right, are less strict. And specifically what they say is that a forward iterator just needs to be an input iterator, right, which requires that if you do star iter, it returns something which is valid and non-void. So we will fulfill the iterator concepts here for these remote pointers, and proxy references are fine. Okay, so just to recap one more time, so these remote pointers can reference memory that lives on another node. They fulfill the random access iterator concept in the ranges library. And we can use them to build a random access range, right? So we could do something like create a subrange where we have two remote pointers that we pass in, and this will work just fine. I do want to point out that naively using them like this might not be the smartest idea, right? Because if this remote pointer is referencing memory on a GPU, each time you dereference it, you're going to be performing a copy operation from your GPU to your CPU and vice versa, which is going to be slow. So this is a nice property, but it doesn't do everything that we want yet. So typically, distributed data structures are going to split up data across multiple segments, right? So whether you have a distributed array, a hash table, or a matrix, right? These many different kinds of data structures, they all have segments, right? And each of these segments is typically stored in a different memory region, right? So if you have a distributed array, it might be split up across a few different nodes. And what we want is a unified concept for accessing all of these different kinds of distributed data structures, right? Typically what is done is somebody implements a distributed data structure, and then they implement some algorithms for the distributed data structure that are specific to the data structure. What we'd like to do is have a level of genericness, like the standard library, where we can implement an algorithm that will work for multiple different data structures. Okay, so our data structure is partitioned across multiple segments. Each of these segments is remotely accessible, and it's located on a single rank. We can access each of these bits of data if we want using these remote pointers. This essentially gives us these are the base primitives that we're working on when we're implementing distributed data structures. Data structures, just to give you some idea of how distributed data structure would be implemented, typically we'll have a vector of segments of some kind, right, where the segments split up your data across many different devices or many different nodes. And then when you want to access a bit of data, for example, a bracket operator where you want to access a particular location within your distributed vector, you go to the appropriate location within this set of segments and then operate on the data. You could build like a normal global set of iterators on top of this, but those are going to be slow and are not necessarily what we want. Yeah. Okay, so like I said, yeah, with iteration, our distributed data structures are now ranges, but this global iteration is slow and not particularly useful. And what we want is a generic concept for distributed data structures and distributed ranges. Okay, so now we're going to talk about that. So I want to start from the bottom up. So if we have, say, a distributed vector, it's going to consist of a bunch of segments. And I want to talk about what this thing highlighted in red is, one of these segments. So what we came up with is that it's a remote range, which is a range with an additional concept of locality, right? Which we call rank using a customization point. So a remote range just has to be a forward range, and then it has to have a rank. So given that we have a range, a remote range, we can say, where is this remote range? And where do we want to operate on it? So this rank customization point returns some implementation-defined information about where the data is stored. For us, it is a weakly incrementable value, basically an integer, that gives the implementation some information about where it's stored. I do think we could formalize this further. But we can now essentially ask, given a remote range, which of my execution agents do I want to execute on? Right? And then we can, if we have, say, that GPU with two different tiles, we can go and launch our kernel on the right tile based on where the data is. Now, a distributed range also only adds one thing. It itself must be a range, but it also has a segments customization point. And what the segments customization point does is it returns a range of remote ranges. What this does is expose the distribution and also the locality of the distributed range. So essentially, you see all of these different segments split up over the different ranks that you have in your computation. So given a distributed range, we basically have two things. We have this global view of our data, and then we have this segmented view of our data. And the segmented view exposes the distribution. And the nice thing about this is that it allows us to use components that we already have, like the ranges library, in implementing our distributed algorithms. So we can basically split up this data and then execute on each of our segments using normal C++ algorithms. Okay, so let's talk a little bit about the implementation. So what we've done so far has focused on essentially this set of concepts along with views that are applied over these concepts, and then two different execution models. A multi-GPU execution model built on top of SYCL, which we call SHP, and then a multi-node, multi-process execution model built on top of MPI, which can also use SYCL to execute on GPUs. Okay, so if we have our distributed vector, like we saw on a previous slide, and we want to make it a distributed range, all we have to do is implement a segments customization point so that we can then go and tell where our different segments are. And so this is pretty trivial for a problem like this, right? We can just go return a view of the segments that exist within our distributed vector, and then that is going to give us all of our different segments. We can also implement global iteration using a join view or some other method, basically by joining together all of these different segments together, right? And then returning iterators to this join view. To implement algorithms, right? Instead of accepting range types into our algorithm, we now accept distributed ranges, right? And then what we're going to do is access data using the segments customization point to see how our data is split up, and then launch data on execution agents that correspond to where the data lives. So for something like reduce, an implementation, a multi-GPU implementation, is fairly straightforward. Essentially, what we have to do is look at our segments using the segment CPO. And then assuming that our segment has data that we want to look at, find out where that data is, go and get an execution policy that will execute where the data lives, and then perform like a reduction operation. What this will do here is launch a kernel on the corresponding GPU that will perform a reduce, right? And then we can add up all of those results at the end. This does get more complicated when you have things like inclusive scan and sort, but essentially it's the same process of operating over your segments, basically propagating your data and communicating partial results, and then copying back into the output. So it does end up being fairly straightforward to implement these algorithms. Okay, now distributed views are particularly interesting, and I think are where this concept really proves useful. So a view in the ranges library, right, takes a base view, which we call V, and then provides a view of that object that fulfills the range concepts. Not all views have a base view, but for our purposes, where we're concerned about locality, we do care about specifically ranges where we like take in a range, or views where we take in a range and then transform it. So we want to know essentially if we have a transform view with some inputs, where does this transform view live? And if it's distributed, how is that data distributed? Okay, so if we have something like transform, we can ask from the standard, what is the base, right? So transform is going to store a ref view inside of it. And then we can then go and ask the ref view, what is your base? Ultimately, this will give us a reference to the stood vector. Now, so if we have, let's start with remote views. So if we have a view whose base is a remote range, then we'd like that view to also be a remote range. What we need to do to make this happen is to implement a rank CPO for it. So basically, if we have a view whose base is a remote vector, we would like for the view to have a rank itself, so that it's also a remote range. So we have essentially two options. The first option would be to implement all these views from scratch and add a rank or segments method, which is not optimal. Or what if we could essentially implement this rank customization point for different library implementations? It turns out that we can do this for many of the views. So if we have a view whose base view is a remote range, then we know that view has to be in the same rank as the base view. So right, if we have a ref view, which is a ref view of a remote vector, it's going to be on the same rank as the original remote vector. So what we can do is go and implement this rank customization point for any ref view where the base is a remote range, right? And then simply call rank on the base to go and get the rank where it's located. For distributed views, things get a little bit more complicated. So we can go and implement a segments customization point for these views, but it does get a little bit complicated for some of them, and there are some limitations. For example, for transform, we unfortunately don't have a way to access the element-wise function that you're performing over the vector with transform. And so given a transform view, what we could do, let me explain this code on the right, is given a series of segments, right, from the base, we could then apply a transform view to each segment, right? That would be equivalent to like a transform view applied to the whole series of data. Unfortunately, we need this fun object, which we don't have any way to get access to. So we do end up implementing our own distributed transform view. Yeah, this fun is an exposition-only private member. It would be nice if we had some way to access it. But what we do as a workaround is implement our own transform view, where we essentially do the same operation, right? We have a series of segments, and then we apply a transform to each segment using this element-wise function. And since it's our implementation, we have access to it. This is still a fairly modular implementation, and doesn't introduce too much code complexity. There are some other views where we can just use like the standard view and then have segments customization point implementation. For example, things like take, drop, slice, etc. I'll comment here. One thing that I really wish we didn't have to do this with is zip. Zip is probably the single most complicated part of our whole code base. If we had a way of getting a hold of all the base views for a zip view, we would be able to implement a customization point in the same way. Unfortunately, there's no way to do that, and so we do end up implementing a zip view in kind of a similar way, which ends up being a little complicated. Okay, so in the SYCL code base, right, in SHP, we can basically execute this standard C++ program that we looked at the beginning. It will be automatically distributed across multiple GPUs. We essentially just have to use this new namespace, right, where these algorithms and these concepts are implemented. And then what this is going to do inside of the reduce algorithm is issue a bunch of calls to this one DPL library, which is going to execute kernels on all of your different GPUs to perform this dot product. In MHP, there's the same situation. There is the additional complexity in MHP, which I don't talk about in depth here, that it is a multi-process SPIMD execution model, which is pretty standard in HPC environments, but does require that basically all of these things be collective operations. So in a SPIMD model, you have multiple processes, and each process is going to execute each line of code. So when we create a data structure, it's a collective call, and all of the different nodes will communicate to move their data around. But other than this caveat, it is pretty much like standard C++. Okay, so I won't dwell too long on this, but we've run a collection of standard C++ benchmarks. By no means do we have full coverage, but we do think this is a really interesting example of how you can build on top of ranges and execute what is standard C++ across multiple GPUs or multiple nodes. So we see good scaling in this scenario. So now I would like to try to do a demo, which is going to be very exciting, I'm sure, because you never know if it's going to work, particularly when you do it live. Okay, so what this thing is that I need to make this much larger, don't I? All right, can we see that? So what this thing is that I'm writing into is a tool called replay, which essentially takes lines of code that you put into it, it goes and compiles them, runs them, and then prints out any lines of input that you have from that particular line of code. This is necessary as opposed to something like Cling, because what we're doing now is running using Intel's OneAPI compiler, which is based on SYCL, using SHP, and we're going to be executing on a system that I think has 8 GPUs using distributed ranges. So we can create a distributed vector like this, and then it is, I'll say again, the reason that it's a little slow is because we have a compilation in this process, right? So for every line I put in, there's a call to Clang++. But so we can create a distributed vector, and then what this is going to do is it's going to create a vector, it's going to allocate buffers on each of our 8 GPUs, and then we have this object that we can use to access them. So this distributed vector, we can use it in places we would use a normal range, like print, right? So what print is doing is just printing it because it's a normal range, right? But we can also access it using segments, right? So we could look and see how this range is actually distributed and say like rank something has segment something, and then hopefully we should see how the data is distributed over our different GPUs. Good. Now, not particularly interesting because we have a bunch of zeros. So let's maybe put some data in our. So we can do something like an enumerate, right? Which is going to take in enumerate view is going to take in our original data. And then it's going to create a view of that data where we have an IOTA view zipped with the original data. And then we can, I don't know, set v equal to I+1, maybe. Hopefully I don't have any typos because the compilation is a while. Great. So then we can print that out again and see what we have. But hopefully this gives you some idea. Basically, you can, at a high level, create these distributed vectors, use standard C++ algorithms over them. And you can also, I didn't talk too much about how this actually works, but you can use multiple distributed ranges together in an algorithm. And we're able to do things like identify when the segments don't match up, and then deal with that accordingly inside of the algorithms. So for example, we can do an inclusive scan where we basically have an inclusive scan operated over V, and then we're writing the output into O, which is a distributed vector that is going to have a different layout, right? Because it's much bigger. It's 500 elements instead of 100 elements. So each of its segments is going to be much larger. Okay. The compilation time is getting a little longer, as you can probably tell, because as we add more and more kernels that the compiler is having to generate code for, the compilation time gets a little longer. But we can just see what the output is here. Okay. Yeah, so we can see that the output from V got written into the corresponding elements of O. All right, let's go back to the presentation. Great. Okay, so I'll talk just very briefly, and I won't dwell on this because we're running a little bit low on time, on dense and sparse matrices and how we can represent dense and sparse matrices using these distributed range concepts. So first off, I'll talk about how you might represent a sparse matrix using a C++ data structure. What's weird about sparse matrices, right, is that they can be represented using many different formats, and each format is going to have a different natural order of iteration, right? If you have a CSR data structure, the natural way to iterate over it is by row, because we have these row pointers which point to where the beginning and end of a row are in a values and a column indices array. So this basically tells us that, oh, row number 1 is located from index 1 to 3, not including 3 in the values and column indices array, and then we can see, oh, we have 2 elements, both titled, both with the value 1 at column indices 0 and 2, right? However, there are lots of other different types of sparse matrices that might have different natural iteration orders, right? For example, COO, you typically have just a set of tuples of values and row and column indices, and then you iterate over those just by individual tuple, not by row. So I've done a little bit of work with the GraphLaws community on developing C++ concepts for sparse matrix iteration. And the basic way that we have iteration by default is just unordered iteration through a series of matrix tuples, similar to the COO. There are more efficient ways to operate over some of the other data structures, but by default, this is the only thing that you can be guaranteed is going to be available for any particular sparse matrix. If your matrix supports a particular type of iteration, you might have some additional customization points, right, that might give you additional ways of iterating through it. Shout out to the graph library proposal where they're exploring some of these techniques for graphs in particular. But what I want to show here is that if we have a representation of a sparse matrix like this, which is kind of a funky data structure, we can represent and operate on it as a distributed range. So distributed dense and sparse matrix data structures typically split up your data into a series of tiles. So you partition your matrix into tiles, and then each tile is going to be stored in possibly a different memory space. And these tiles could be sparse if you have a sparse matrix, or they could be dense. Each tile represents a submatrix, right, of your matrix. And in a distributed matrix, what we can do is say that each tile satisfies remote range. So that we can then go and look, right, if we have a particular tile, tell me where that tile is, and you can also do things like copying the tile to your local memory space so you can operate on it more efficiently. By creating a range that returns all of these tiles, right, we can implement a segments customization point for our matrix, right? And then what this allows us to do is use one of these matrix data structures with the normal range algorithms, right? So we can do something like have a distributed sparse matrix and then apply algorithms and views like transform and reduce on a matrix, which I think is pretty powerful. One thing that I kind of am glossing over here is that there is this distinction between a tile view and a global view of the elements within a particular tile, right? Typically, when you operate on one of these tiles, you use local indices instead of global indices. And so there is an index transformation required in the segmented view. OK, so just to recap, right? Standard C++ has all of these great things, data structures and views and algorithms that we can combine together to write code that is both high level and also able to be executed on hardware from different vendors, right? And to get good performance. Ranges are the glue that hold all of this together. And so when we think about distributed data structures, I think we need to be thinking about what are the concepts that hold together our distributed data structures and what do we want out of those concepts. In terms of lessons learned, right, the ranges library provides a lot of useful tools to build on top of. I think also the general design of using customization points is particularly powerful. and enabled us to do stuff here that would be very, very difficult otherwise. It reduces a lot of kind of repeated implementation that would otherwise be required. And also, we can build on top of it. We can take ranges concepts and then refine them to add things like distributed and remote ranges. Now, while ranges has almost everything we want, right, to build on top of, there were a few things that would have been useful, right? So we ended up building some views from scratch. In particular, I don't know if there may be compelling reasons that this is not the case, but it would be useful if every view exposed its bases, including zip, right? This would truly allow us to use just customization points and then use like the raw library provided set of views for all of our views and just build on top of them. It would also be nice, right, if there are things like a predicate or an element-wise function that are an input to the view, if those were also exposed. Because I think those are very useful for libraries like this that are trying to build on top of ranges. Limitations. So I did not talk at all about distributed iterator concepts here today. We do have a distributed iterator concept, but it is not as complete and nice as this distributed range concept. I do think that if view iterators exposed base iterators, which are currently just present in the view iterator implementations as like exposition-only private members, that would do a lot towards allowing us to have like an expressive distributed iterator concept that allowed us to support both the iterator interfaces for the algorithms and the ranges interfaces. We do support some of the iterator interfaces in our code, but it's not as complete as we would like it to be. Another interesting question that we're trying to explore is how does this work if we have nested ranges, like a distributed range of distributed ranges? Given that our ranges can only have trivially copyable things inside them, this is a bit of a challenge, but I think it's important to examine. Of course, this is a research prototype, although we're working to get this more and more complete, and so we don't have full coverage. And also, I think there are interesting opportunities for formalizing this concept of locality and like where a range lives beyond this kind of integer, right, that our rank returns, which gives us some implementation to find information about where this data lives. Okay, so just to wrap up, we've tried to extend ranges to support distributed data structures, right? Ranges unites data structures, algorithms, and views, and I think it's important for distributed data structures to have something like that as well. We can build on top of vendor-supplied algorithms to get competitive performance. Our work is open source, so please do check it out, and we would love to talk to you about any interesting use cases or problems that you have, data structures or algorithms that are particularly useful for you. And with that, I will open it up for questions. But thanks very much, everyone.
So I have first of all, I think it's just kind of a really cool topic, and excited to see it. So I have a few questions. So how are you addressing zip operations and transformation that span different ranks? They don't have compatible segmentations and things. How do you address that?
That's an excellent question. So do I need to repeat the questions, or can they hear on the mic? I'll just repeat. So the question was about zip and basically how we handle cases where you have a zip view and either the ranks are not compatible or the segment sizes are not compatible. And so you have different cases. So in the GPU scenario, it's actually fairly simple because we have like load store semantics for memory on other GPUs. And so we can simply slice up our zip view so that we have a series of we have a series of ranges that are only on at most like 2 different ranks, and then pick one of those ranks as the place where we want to execute. That's how we do it on the GPU side. And so there is going to be implicit communication that happens when you execute on one of those GPUs, right? It's basically going to be using like normal load store to read out of another GPU's memory, which is fairly efficient, like while you're executing that kernel. For multi-process, it's more complicated because you don't have like efficient load store semantics for another process's memory, typically. So there are basically two things that we can do. You can either basically execute on one of those processes and then like read those values individually, which is not particularly efficient, or you can try to do something smart like copy them all over. In practice, the segments tend to be aligned, so we don't have this problem as much, but it is one of the more interesting and complicated parts of this. So.
Okay, so actually, I do have a follow-up on this thing.
Yeah.
So, and I guess I do come from more of a kind of distributed computing that's more NPM deep as opposed to kind of GPU space. But in that space, you typically have to deal often with like redistribution, data segmentation. So you end up having a lot of segments. The random access no longer linear, or it's quasi-linear, and so on. So have you thought about that space, or that's kind of not that much your cup of tea, and kind of what are your thoughts in that direction?
So do you mean more in terms of like redistributing data based on
right? So
like load balancing?
If you do a sort, or if you do kind of any operation that kind of requires a lot of data exchange, what are your thoughts in terms of like who's supposed to deal with that part?
Yeah, so that's an excellent question. So when you do sort, you might actually want to change your distribution, right? Because you might have a distribution that is somewhat like skewed. Typically, you want to do something like a partition sort, right? You look at your data, and then you figure out like what am I going to pick as my like partition points for all of my different segments, and then you like send your data to a particular node based on that, and then do a local sort, and you're done, right? What we currently do, because the sort API, the user provides both the input and the output. We essentially like redistribute the data using possibly a different distribution, and then at the end we copy into the final output. And we don't currently like have a mechanism for like changing the distribution of a distributed range, but I think that is something that would be useful, and like maybe we should look into. Yeah.
Thanks for the presentation. I'm just curious, thinking about the implementation of your distributed data structures, can you implement all of that in just standard C++ and compile it with an off-the-shelf compiler, or do you need to get special compiler support somewhere along the way?
Yeah, so what we depend on more, I mean, for the GPU stuff, we depend on a compiler that can compile like GPU kernels. So we run using Sickle, which can be implemented using C++, standard C++, but typically, like if you want to run on GPUs, there's a compiler extension that compiles that. So for the multi-GPU implementation, we depend on Sickle. For the multi-node implementation, we just depend on MPI. And so you can compile like with GCC, standard compiler, and just the MPI library.
Thanks.
Yeah. Okay, well, thanks everyone.